Okay, I think we'll get started. So today we're going to talk about valence bond theory, and we'll just give an overview today and then introduce this idea of hybridization. And then next time we'll do what we call a complete bond description in the valence bond theory. Now, valence bond theory is probably it's the simplest theory of bonding that gives geometric shape. So we have the Lewis structure, which is a theory of bonding, but it is just giving connectivity. So valence bond theory is the first time we get to a point where we can describe the three-dimensional structure of the molecules. And this is the theory of bonding that we'll talk about in this course. As we move further through the curriculum, we will be talking about more sophisticated theories of bonding, in particular molecular orbital theory. But we will not be talking about that here. We will limit ourselves to valence bond theory. Now your book, if you have a Gen Chem book, will focus also on valence bond theory. It may have a section or two on molecular orbital theory, and certainly be fine to compare and contrast that. You just want to be careful that you know what theory you're in when you're thinking about the theories. All right, so the key idea for valence bond theory is that the bonds form by overlapping orbitals of the valence electrons. So we only care about the valence electrons, and we overlap those orbitals in order to put electron density between the nuclei. So the nuclei are positively charged, so they're going to have a repulsive force between them and want to push themselves apart. So we need to get some electron density in between those nuclei. So the atomic orbitals, we know, are describing where the electrons are. And those for the valence electrons are describing where those outer shell electrons are. And as one atom comes closer to another, we can get overlap of those orbitals. Now, in valence bond theory, we just take that as overlap. In more sophisticated theories, we have to be a little bit more careful about how it overlaps and all sorts of different more serious quantum chemical ideas. But here we're just looking for overlap of those orbitals. Now, we will suffice to think about two basic types of overlap. We can overlap orbitals end-on like this, and we get some overlap here. The nuclei are right here. So here and here are the nuclei. The orbitals describing the positions of the valence electrons are protruding in this direction for this atom, this direction for this atom, and they overlap in the middle. And so we have a positive charge here, wanting to repel, but there's an attractive force to all those that electron density in between those two nuclei. And if the molecule bonds, then that attractive force wins out over the repulsive force. Bonds where the electron density is between the nuclei are referred to as sigma bonds. Now, we can have orbitals, because we know about the p orbitals, they can come in side-on like this and overlap. And when they do that, the nuclei are here. So here's the nuclei. Here's nuclei. Positive charge, positive charge. Now they're going to want to repel, but there's a net attraction to the electron density that's above and below the bond axes. Now, there is a bare open area here, so this is less significant than this. So this type of a bond is relatively weaker than this type of a bond. When the electron density is above and below the bond axis, we refer to that as a pi bond. All right, so we try to get these orbitals overlapping for all of the elements that are in the Lewis structure for a molecule. And this will take, and when we consider then the three-dimensional shape, then this will take us from the Lewis structure to that 3D molecular shape. And that's where chemistry happens, right? Chemistry is a three-dimensional thing. All right, so what are the ingredients of the theory? Well, we have the atomic orbitals. So we've learned about these before. So we have S-type orbitals, P-type orbitals, D-type orbitals, of course F and G and so on, but these will be the main players, and in fact S and P will primarily be the main players, but we will need D as well. So we have the atomic orbitals. Now those are showing where the electrons are. The Lewis dot structure shows how the atoms in the compound are connected. So each of those atoms has their own valence electrons. They have now brought that to the molecule through the rules and algorithm for the Lewis dot structure. But surrounding each of those atoms are these atomic orbitals. And so we have the ability to think about where the electrons are. We now have the connectivity. And then we have the idea we talked about last time, and that is these sources of electron density, whether they're bonds or lone pairs, want to try to get as far apart as possible. And that gives us our three-dimensional geometry. So with these three ingredients, we're able to construct a theory of bonding that goes beyond just the connectivity of the Lewis dot structure to the actual shape of the molecule in 3D space. All right, well, the central idea that we will talk about today, the main thing for today, is this idea of hybridization. So we have a little bit of a problem to reconcile the atomic orbitals geometry and VSEPR geometry. So let's just think for a moment. We've got the s orbitals, which is completely spherical, right? Then we've got the p's that are oriented like this, and then right at you. So px, py, pz, like those three in the three orthogonal directions, px, py, pz. But we have to create things like trigonal planar or tetrahedral. These are not orthogonal to each other. They're 120 degrees here, 105.7 degrees here, and so we have to make the geometric structure that is dictated through the principles of valence shell electron pair repulsion, these guys getting as far apart as possible. So what we need to do is make what are called linear combinations of the P's, the S's, and then sometimes the D's. When we get to the trigonal bipyramidal and the octahedral, we need to include the D's as well. And this process is called hybridization. So let's talk about that. So one of the big principle is whatever number of orbitals you start with in your hybridization process, you get that many orbitals out. Now, we have to make all the different geometries. We have to make the linear geometry. So let's start with linear. The hybridization scheme there is called SP. So we say the atom in this atom is SP hybridized. And what does that mean? It means the four total orbitals, S, Pz, Px, Py, have now become four orbitals, two of which are SP hybridized. Okay, now we'll go through this first, then we'll come back here and we'll show how that hybridization occurs, what that actually means. Okay? But the key idea here, we're going to take the S and the PZ and hybridize them as SPs. Now, I'm going to be doing a specific set of combinations. Other authors might do things a little bit differently. The main takeaway here is that this is an S and a P. You really have the choice to choose any of those. Usually, people take the bond axis to be the z-axis. So if you want to make an SP hybridized orbital, and this guy's getting ready to bond, overlap this orbital with something else, then that would be the bond orbital. And that's the motivation for choosing the PZ instead of the PX or the PY. But again, it doesn't really matter. as long as you're clear in what you're doing if you're talking to somebody else. Okay, well, the remaining orbitals just come along for the ride. So in our case, the px and the py come along for the ride, but they're important. They're there. So we've used one of the pz. I'll put it like this, actually, because there's our pz, right? So then on this atom, there would be the px and the py still sitting there. So we would have two orbitals, one pointing this way, one pointing this way, and again, we'll see why that happens, why they point that way in just a bit. But then the remaining orbitals would be like this, and then coming straight at you. Okay? And that would all be on this central atom. All right. Now, if we need to make three, so if we need to make trigonal planar, okay, then we have to take an S and two of the P's to make three sp2s. And this is an sp2 hybridization scheme. So we'd say, what's the hybridization scheme? It's an sp2 hybridization scheme. And the py just comes along for the ride. And so this this atom has been sp2 hybridized to create three hybrid orbitals, three distinct sp2 hybrid orbitals, and then one p orbital is left. And that's going to be protruding up out of the plane. Because let's think about this. If I choose, and again, I kind of have free choice here. I'm choosing the pz and the px here. So that's going to create the xz plane, and that's going to leave the py free. And again, it doesn't really matter which two we choose. Okay, so that'll look like that. But regardless of which two we choose, the other one will be perpendicular to the plane made by those two. Okay. So it looks something like that. All right, well, let's move on. Now, if we hybridize the S and all of the P's, then we get something called the sp3 hybridization scheme. And that's necessary to make four orbitals. Right? We make four new orbitals. All of them are sp3. They're all equal now. There's no leftover P's, and they are oriented in the tetrahedral shape. So they take on the correct geometry. And again, well, we'll show for these two, we'll show how the actual geometries come about. And then for this one, we'll just kind of have to take it that this is going to be tetrahedral. Okay. All right, well, that will take us up through tetrahedral molecules, but we know we have trigonal bipyramidal and we have octahedral, and there we run out of P's. So in order to continue our hybridization scheme, we have to include D's. And so right off the bat, we know that any molecule that has as a central atom an element from the second row doesn't have any D's. So it wouldn't be involved in a trigonal bipyramidal or octahedral. We'd have to get down into the n equals 3 or higher to get a 3 D's starting to come in. All right, well, let's see where we get these. We get S, all of the P's, and I'm choosing here now the dxy. Again, different authors might choose different things, and it doesn't, again, much matter. So there's 1, 2, 3, 4, 5 orbitals. So we get 5 identical orbitals, 1, 2, 3, 4, 5, and these are all named sp3d. So the hybridization scheme here is called sp3d hybridization. And that gives rise to trigonal bipyramidal. And so these will come out in the necessary geometry. And we won't go into seeing how that geometry comes out, but so I'll just tell you that's what happens. So we come out in the trigonal bipyramidal hybridization scheme. So each one of these tan orbitals is an sp3d orbital. There's 5 of them. And then finally, for octahedral, we need 2 more Ds. So we have S, 3 of the Ps, that's 4, 2 Ds, that's a total of 6. I didn't write them all out here. So sp3d2 times 6, that's the set of all the orbitals, and that's then called sp3d2 octahedral geometry. And that looks something like this. It's in the octahedral shape. 6 identical hybridized orbitals in the octahedral orientation. All right, well, let's come back now to how the scheme actually gives rise to the correct geometry. So let's start with the SP, and I'm going to erase this over here to give some white space to draw these. And we have to go back and really remember our atomic orbitals. It's so critical to know those atomic orbitals. So if you aren't there yet, make sure you go back and really understand those atomic orbitals, what they mean, how to draw them. That's just critical for so much chemistry. It really is quite remarkable how we can solve the theory, the quantum mechanics, for hydrogen, just hydrogen, and with that information alone, what those atomic orbitals look like, we can construct a whole theory of bonding and really do an awful lot of chemistry. And even practicing professional inorganic and organic chemists are using Lewis structure, Vesper theory, and valence bond theory every day, and it's all based on these hydrogen atomic orbitals. So it's not just a passing thing in your Gen Chem book. It permeates throughout all of chemistry. So really get those atomic orbitals down. All right, so let's look at how we make an sp hybridized orbital. So we're going to take an S and the pz. Right? So let me draw my s orbital, and I'm going to put the positive sign here. This is not charge. Remember, this is telling us the sign of the atomic orbital. And in these little models, the sign is, say, pink is positive, purple is negative. Okay. So we have the s orbital here, and we have the pz orbital here. Okay. Now this nucleus, this is we have only one element, so this is right on top of this, right on top of that. These are together. These are the same nucleus. So we can combine these or make what's called a linear combination. Here's our set. We'll make a linear combination. And we're free to do this any way we want, but there's kind of 2 obvious ones, and that is to take S plus PZ. Okay, what is that going to be? Well, that's going to be an sp orbital, and what's it going to look like? It's going to look like because let's think in pictures here now. These are on top of each other, and I'm going to add them together. So up here, we add constructively the atomic orbitals, or the wave functions, add constructively above the nucleus, and they add destructively below the nucleus. And we create an orbital that looks like this, just like that. Okay, so that's one of them. Okay, well, how are we going to get the one that's pointing downward? We need this one now. Well, let's just take the subtraction of P from S. So S minus PZ equals an sp orbital, but this is pointing downward. Now, this is our new set. Okay, that's our new set of orbitals. So we've gone from these two to these through via this positive and negative linear combination. Well, let's draw them then on the same nucleus and verify that we get a linear. Do a better job than that. Let's see. We'll verify here. We've got one of them here, one of them here. And yes, indeed, this is prepared now. This is prepared now to bond. If I have another one coming in, I can overlap those. And I can do so from this side and from this side, or on the board here, from the top and the bottom. So these are prepared to bond out from here and create a linear geometry around this atom. Okay, I think that's all. Oh, no, I need to say a bit more. So coming out of the board, right, out at us is the, say, px, if this is the x direction. Z will go x, this will be y. So there's a p orbital coming out of the board. So this p orbital, going to point right at you, and then it's going to come out of the board with the center, right, the node, sitting right on the nucleus, in and out of the board. And then we have the py, which will be sitting right there. So let's draw the py in. I'll draw that in green. And remember, this now has a sign. Notice this is plus and plus. This will be, oh wait, let's see. Yeah, this is plus and plus. This is plus and minus, or pink and purple, because this is a pz orbital, or this is the py orbital. Right? And these are the sp hybrid orbitals. And then there's one more py coming out of the board. And so this is prepared to make a linear molecule, and then when it does, it has, so let's say I make my molecule this way, then I'm going to have a p orbital going above and below, and then a p orbital coming in and out. Okay, and those can bond then from all those directions. Okay, well, let's do a little bit harder one. Let's do sp2. The good thing is it will stay in the plane, so it will be easy to draw on the board. And then once we see this, we'll just have to kind of accept these 3D ones. They get pretty tough to draw on the board. All right, so what do we have? We have S, let's go PZ and PX, okay, like I've done here. Okay, I'll change things on you a little bit. The X direction, let's put our axes here. So there's Z. Now we'll have the X-axis in the board here. And the Y-axis will be coming out at us. Okay, so we've got an S. We've got the PZ. And then we've got the PX. So S, PZ, PX. Okay, I need to make something like this, right? Trigonal planar, because that's our scheme here. So trigonal planar. This is the XZ plane, and py will be sticking out right like that. So py will be coming at us. So let's wait on the py for a moment, and let's try to construct these. All right, so let's look at S plus PZ plus PX, and that's going to be an SP2. Okay, let's see where that is. So if I draw my nucleus here, I'm getting, I'll dash these in. So this is plus here, plus here. So I get constructive interference up here, destructive interference here, and then I get plus over here. Okay, it's getting really messy here, but so I have constructive here and here, destructive over here. And so we can kind of think about it as adding vector components, x, z in this direction and x in this direction. Where are we going to get the most positive overlap? It'll be up in this direction. Okay, so based on these pictures, if I add them all, I will get this guy. Okay, well, what if I want the one pointing down? Okay, let's try that one. Maybe I'll change colors here. So let's go red. We'll go S plus minus PZ, because I can point it downward here now, plus PX. Okay. Well, that's going to go like that. Okay. Now, a little bit of a trick question. Where's the next one? It has to go this way, right? And nothing says in a linear combination you can't have 0 here. So you can think of it, it's sort of tricky, but you can think of it as I have S plus 0 PY, and then I want minus PX. So let's try this one. S plus 0 PY, or PZ, sorry, PZ, minus PX. Okay. And what's that going to look like? That's going to look like this. And so that gives us the correct hybridization for this sp2 hybridizing. Now, this is just one manifestation of this. So it doesn't mean these are always these combinations. So maybe as a little challenge for you, we've got it like this, we may need it like this. Okay. So see if you can make the correct linear combinations to get something like that, and then maybe try this and this. Okay. So you can rotate this any way you need it to come in and bond with something else by just tweaking the linear combinations. So this set here is the set that will make it look like this. Okay. All right, well, we've got P's now coming out. So that's going to be really hard to draw here, but we'll have a P coming, one P coming out. So that's just going to be coming out like this and like that. So let me take this and turn it on its side. So here it is like this. I'm going to turn it this way, and then our P will be sticking up. So how would we draw that? We would usually just draw the P, right? And then in this plane here would be this. Okay. And so you have to kind of think in a couple of pictures, and then your head sort of put them back together as you start saying, where are these orbitals to bond? Okay, well, that's enough for this. The next video, which I encourage you, you can go right to the next video now, because the two together form a coherent story. Then you can come back, practice some of this. The next video is going to talk about what we call the complete bond description. So we will go from the Lewis structure to the correct hybridization, and then describing what the bond is. Okay, so that will complete the story then of valence bond theory.